All right, let's just jump right in. We're going to do a super quick tour of, well, pretty much everything. The basic rules that run the whole show, from giant galaxies all the way down to the tiniest little bits of matter.
Okay, so let's start with where you are, right this second. Simple as this, you're on a rock.
And this rock, it's not tied to anything. It's just floating. Actually, it's hurtling through this insane, empty vastness we call space. So you've got this rock, and it's surrounded by, well, a few other rocks, some gas clouds, and just a whole lot of nothing. Seriously, it's mostly empty out there. Which kind of makes you wonder, right? Like, what the heck is going on here? And to even begin to answer that, we've got to look at the rule book for the universe, and that rule book is called physics.
So where do we start? Well, let's go back to the guy who basically wrote the first chapter of that rule book, the OG gravity guy himself, Sir Isaac Newton. Newton came up with this. Honestly, it's a beautiful little equation. F equals ma. Force equals mass times acceleration. And this little thing, it completely changed how we see the world.
So here's the magic trick. If you know all the forces, all the pushes and pulls acting on something, you can predict exactly where it's going to go. I mean, perfectly. Doesn't matter if it's a basketball, a car, or an entire planet. Newton's big aha moment was realizing that the same thing that makes an apple fall from a tree is what keeps the moon circling the Earth. It's all gravity. And the rule is pretty simple. The more stuff something has, the more mass, the stronger its pull. But, and this is the important part, that pull gets way, way weaker the further away you get. And that's the secret to orbits. It's this beautiful dance. A planet is constantly falling toward the sun because of gravity, but it's also moving sideways so fast that it just keeps missing. It's basically in a state of perpetual freefall, forever.
Okay, this brings up something people mix up all the time: mass versus weight. Your mass is how much you there is. That number doesn't change whether you're here or on Jupiter. Your weight, that's just how hard gravity is pulling on you. So hey, listen, you're not overweight, you're just on the wrong planet. All right, so Newton's rules are amazing for things moving around. But what about when stuff stops, or breaks, or gets hot? To figure that out, we need to talk about the currency of the universe. We need to talk about energy. So you've basically got two main types. Just think about your phone for a second. When you're holding it up, it's full of potential energy. It's just stored up, waiting. The second you let go, that potential energy turns into kinetic energy, the energy of motion. And yeah, it's that kinetic energy that makes your screen go crack.
You know, it's funny, because in physics, the word work has a super specific meaning. Energy is the ability to do work, but you only do work if you actually move something. So get this, you could push against a brick wall with all your strength for an hour, sweating, getting exhausted, and in physics terms, you've done zero work. Nothing, because the wall didn't move.
Now, one of the biggest rules about energy is you can't make it or destroy it, but it does have this tendency to just spread out, to get messy. That's a concept called entropy. It's the universe's one-way street toward total disorder. It's why your coffee gets cold and why an ice cube melts. A puddle of water is never going to just decide to pop back into a perfect ice cube. The universe just doesn't work that way. It prefers chaos.
Okay, so besides gravity, there's this other huge force running the show, electromagnetism. And the rule is super simple. You've heard it before. Opposites attract and likes repel. Positive wants to hang out with negative, but two positives, they want nothing to do with each other.
And for a good long while, it seemed like we had it all figured out. Newton's laws, energy, electromagnetism, it all just worked. But then, scientists started looking really, really closely at light. And that's when things started to get weird, like really weird.
That number, that's the speed of light. It is the ultimate cosmic speed limit. Nothing can go faster. But here's the bizarre part, the part that breaks your brain. That speed is the same for everybody. It doesn't matter if you're standing still or flying in a rocket at half the speed of light, you'll always measure light moving at that exact same speed. How is that possible?
Well, that one stubborn fact is what led this guy, Albert Einstein, to basically flip the table on all of physics. He realized that if the speed of light never changes, then something else has to. And that something else was everything we thought we knew about space and time.
I mean, he just blew everything wide open. He said space and time aren't fixed, they're flexible. They can stretch, they can shrink.
He told us gravity isn't a force pulling us down, it's actually the shape of space and time being bent by massive objects. And then of course there's his most famous hit single, E=mc², which showed that mass and energy are really just the same thing in different outfits.
But here's the funny thing. While Einstein was figuring out the universe on the grandest scales, he accidentally kicked open a door to a whole other realm that he kinda hated. The totally bizarre world of the super, super small. Welcome to quantum mechanics.
Down here at the quantum level, the rules just go out the window. Little particles like electrons, they don't really have one spot where they exist. It's more like they exist in a cloud of maybes. They're in a state of being here and there, and pretty much everywhere else, all at once, until you look.
And no, this isn't because our equipment sucks. It's a fundamental rule of the game. It's called the uncertainty principle. Think of it like a cosmic seesaw. The more you know about where a particle is, the less you know about how fast it's moving. And the more you know about its speed, the less you know about its location. You can't have both, ever.
Okay, and if you thought that was weird, hold on. The act of just looking at something changes what it does. Seriously, a particle will behave like a wave, spreading out and doing multiple things at once, but only when you're not watching. The moment you try to measure it to see what it's doing, bam, it snaps into focus and acts like a normal little particle, picking just one path. It's like it knows you're looking.
So think about where we've been. We started with Newton's universe, which was like a perfect, predictable clock, and now we've ended up in this quantum world of pure probability, where nothing is certain until we look at it. Which leaves us with one last, kind of spooky question to chew on. If reality only solidifies when we observe it, what is the universe actually doing when nobody's looking?